The wind cut different across the Montana prairie. John M. learned that his first winter in central Montana in 1892, when his cabin interior dropped from 55 degrees to 45 degrees in just 3 hours after the fire died, and he had to rise at 2 in the morning to add wood or watch frost form on his windows. He had built his cabin exactly the way every homesteader on the Great Plains was told to build it: tight log walls, standard open hearth, continuous fire tending through the night, proven and trusted. Across the high prairie, settlers were fighting the same losing battle in cabins built by the book and failing by the season. Over the next 2 years, John quietly applied an old-world technique behind his fireplace that kept his cabin at 65 degrees through the night with the fire completely dead. What did he understand about storing heat that every serious builder today should know? The upland prairie of central Montana stretched in every direction from John's timber claim, a landscape of newly cleared stumps and hard-frozen clay soil that cracked like pottery when the temperature dropped below zero. The nearest railhead sat 12 miles east, meaning fresh lumber arrived by wagon when the roads weren't drifted shut, and local timber meant whatever oak and pine a man could fell and split himself before the deep cold set in. By December of 1892, the wind swept across snow-crossed cattle pasture with nothing to break it, carrying temperatures that regularly hit minus 20 degrees Fahrenheit and stayed there for days. Every homesteading manual John had read, every conversation with the county land agent, every piece of advice from established settlers pointed to the same proven system: build your cabin with hewn or sawn logs, chinked tight with mud and moss. Place your hearth in the center with a tall cast iron stove or brick fireplace. Seal the gaps, trap the hot air inside, and tend your fire through the night. The Northern Plains. Homesteader's Guide, published just 2 years prior, dedicated an entire chapter to this approach, recommending that settlers light their fire each morning, bank it when they retired, but expect to rise in the dark to add fuel because overnight, cooling in frontier cabins was simply the price of prairie living. John had followed these instructions precisely when he raised his cabin that spring. The walls stood solid, built from oak logs he had felled himself, each gap packed with clay and prairie grass, according to the manual's specifications. His fireplace occupied the center position, constructed from local limestone with a proper draw that pulled smoke cleanly up the chimney. The door fitted tight, the single-pane windows sealed with putty, and the whole structure looked exactly like every other successful homestead cabin in the territory. But success on paper proved different from success in practice. Beyond the temperature drop he had already experienced, John noticed that his water bucket froze solid, even when placed just 3 feet from the fireplace. The interior walls themselves grew cold to the touch by midnight, and frost collected on the inside surface of his windows despite the sealed construction. His neighbor to the south, Samuel Roberts, reported identical problems in his own cabin built the previous year, rising twice each night to add split wood and still finding ice in his wash basin come morning. Mary Harris, the widow homesteader whose cabin sat a quarter-mile north, burned through 10 gallons of lamp oil each month just trying to supplement her hearth's heat during the coldest weeks. The fuel consumption troubled John most of all. His calculations showed he was burning nearly 3 cords of split oak each month just to maintain minimal overnight warmth and still the cold cut through his walls. At this rate, his carefully stockpiled winter wood supply would run short by February, leaving him dependent on expensive rail-shipped lumber or dangerous trips to cut green timber in sub-zero weather. The mathematics of frontier survival weren't working in his favor. Sitting by his inadequate fire on a particularly bitter evening in late December, John remembered stories his grandfather had told about the old country. Johann Müller had immigrated from the German territories in the 1840s, bringing with him memories of thick-walled houses, where massive masonry stoves heated entire rooms for hours after the fire died. These weren't simple fireplaces, but heavy stone constructions that absorbed heat during burning and released it slowly through the night, requiring far less fuel than the American frontier method of continuous fire tending. The memory connected with observations John had made that previous summer, while trading horses with members of the Crow Nation. He had noticed that their buffalo hide winter lodges incorporated thick stone or earth backing around their central hearths, creating walls that held warmth long after the embers cooled. The Apsailuk people had survived plains winters for generations using these thermal principles, yet the homesteading manuals dismiss such methods as primitive or impractical for permanent structures. John began sketching plans for an experiment. Instead of relying solely on his cabin's log walls and continuous fire, he would construct a massive stone wall directly behind his fireplace, extending 3 feet thick and rising 8 feet high inside his living room. This wall would sit adjacent to and behind the hearth, positioned to absorb the fire's heat and store it in stone mass rather than letting it escape up the chimney or dissipate into the cabin's thin walls. When word of his plan reached the local timber supplier, Foreman Thomas of the cooperative dismissed it as wasteful over-engineering. "Stone here?" Thomas argued during a supply run. "You'll freeze because stone soaks up your heat and loses it straight to the outside. That's why we build with wood. It insulates." The church reading circle picked up the story and began referring to John's project as a castle wall in a simple log cabin, joking that he was building fortifications rather than practical winter shelter. Even Anders Johansson, the Scandinavian mason who had helped several homesteaders with their foundations, expressed skepticism about the thick interior stone construction. "In the old country, yes, but here on the prairie with your hard winters and wind, you need every bit of heat moving through the room, not trapped in heavy stone," Johansson warned. The consensus among experienced settlers remained clear. John was violating proven frontier wisdom by attempting to adapt Old World techniques to New World conditions. But John's grandfather's stories and his observations of indigenous thermal management suggested a different possibility. Heavy stone might not trap heat uselessly. It might store heat efficiently and release it gradually, creating a thermal reservoir that could carry a cabin through the long prairie night without constant fire tending. The principle seemed sound, even if the local application remained untested. On the last day of December 1892, John completed his stone wall construction with help from Herr Klein, a German-Swiss mason who understood the old country techniques, despite his own doubts about their frontier application. The wall stood solid and massive, its limestone blocks fitted tight with minimal mortar, creating a thermal mass that weighed several tons and extended deep into the cabin's interior space. That evening, as wind howled across the frozen prairie and temperatures plunged toward minus 25 degrees Fahrenheit, John built his fire as usual, but resolved to let it die completely before midnight. He would test whether traditional thermal mass principles could replace the accepted frontier method of continuous fire tending. The experiment would either prove his neighbors right about wasted heat and frozen mornings, or demonstrate that Old World wisdom and indigenous knowledge could transform prairie winter survival. The foundation work had begun in November, before the ground froze solid, with Herr Klein directing John through the precise engineering that German masons had perfected over centuries. They excavated 18 inches deep and 4 feet wide, creating a stable base that would prevent the massive stone wall from shifting during the freeze-thaw cycles that destroyed inadequate foundations across the prairie each spring. 6 inches of crushed limestone went down first, compacted with wooden tampers until each stone fragment locked tight against its neighbors. Above this came 4 inches of sand mixed with gravel, wetted and compacted again, until the entire base formed a solid platform that would distribute the wall's weight evenly across the clay soil. Klein selected limestone blocks from a quarry 8 miles southeast, choosing stones that had survived at least one winter in the ground without cracking, a test that revealed their ability to withstand repeated temperature changes. Each block measured roughly 12 inches by 8 inches by 6 inches, sized to fit a man's grip but heavy enough to create substantial mass when stacked. The dry stack technique Klein demonstrated required no mortar between most joints, instead relying on careful stone selection and precise fitting so that each block transferred its weight cleanly to the stones below. Where mortar became necessary, Klein mixed locally burned lime with sand and a small amount of clay, creating joints no wider than 1 inch that would conduct heat efficiently rather than insulating between stones. This contrasted sharply with typical frontier stonework, where thick mortar joints often acted as thermal breaks that prevented heat transfer through the masonry. Klein's approach ensured that when fire heated the wall's interior surface, that heat would conduct deep into the stone mass rather than remaining trapped at the surface. The most unusual element came from John's conversations with Yellowfeather, a Crow elder who had observed the construction progress during a December trading visit. Rather than ending the stone wall at floor level, Yellowfeather suggested extending the thermal mass downward into the floor plane itself. Plains Lodge builders had learned that heat radiates not just upward and outward, but also downward, and that capturing this downward radiation could warm the living space more effectively than letting it disappear into the ground. Following this guidance, John and Klein laid a stone slab 6 inches thick that extended 1 foot beyond the hearth in all directions, creating a thermal floor that would absorb heat from above and radiate it back into the room throughout the night. Frontier builders typically dismiss downward heat as wasted energy, but indigenous knowledge recognized that all directions of heat transfer mattered in the battle against prairie cold. The first real test came on January 3, 1893, during a clear night when outside temperatures dropped to minus 18 degrees Fahrenheit with minimal wind. John built his fire at 6:30 in the evening using split oak, feeding it steadily until the flames reached their maximum height and the stone wall's inner surface glowed with absorbed heat. He continued burning at full intensity until 9:30, when his improvised thermometer showed the wall's internal temperature had reached approximately 400 degrees Fahrenheit. At 9:30 sharp, John allowed the fire to die completely, banking no coals and adding no fuel for the night. This represented a complete departure from standard frontier practice, where settlers would bank coals and plan to add fuel during the night. Instead, John relied entirely on the stored heat in his stone mass to carry the cabin through the long prairie night. The results contradicted every prediction made by his skeptical neighbors. At midnight, 3 hours after the fire died, John's thermometer showed the interior room temperature holding steady at 68 degrees Fahrenheit. The stone wall radiated gentle heat that could be felt 6 feet away, while the extended floor slab warmed the air near the ground where cold typically settled first. By 6 in the morning, 9 hours after the last flames, the interior temperature measured 65 degrees Fahrenheit, representing only a 3-degree drop over the entire night. Sam Roberts, whose cabin sat 400 yards south, had burned 2 full cords of split wood that same night using the standard method of continuous fire tending, yet his cabin still dropped to 42 degrees Fahrenheit by dawn. Mary Harris reported similar fuel consumption with similar temperature losses, confirming that John's experiment had achieved something unprecedented in the territory's homesteading experience. The fuel comparison proved even more dramatic than the temperature maintenance. John's total wood consumption for that 24-hour period measured 1 cord of split oak compared to the 2 cords his neighbors typically burned for equivalent time periods during comparable weather. This 50% reduction in fuel use translated directly into extended winter survival, reduced labor splitting and hauling wood, and decreased dependence on expensive imported lumber when local supplies ran short. The mechanism behind these results challenged fundamental assumptions about stone construction in cold climates. Rather than acting as a cold sink that drew heat away from the living space, the massive stone wall functioned as a thermal battery, storing energy when the fire burned and releasing it gradually through radiation and convection as the night progressed. The stone's high specific heat meant it could absorb enormous amounts of thermal energy without dramatic temperature increases, then surrender that energy slowly as the surrounding air cooled. Klein's precise masonry techniques proved crucial to this performance. The tight joints and minimal mortar allowed heat to penetrate deep into the stone mass rather than remaining at the surface, while the solid foundation prevented settling that could create gaps where heat might escape. The indigenous-inspired floor extension captured heat that would otherwise radiate uselessly into the ground, redirecting it back into the living space where it contributed to overnight comfort. Word of these results spread quickly through the homesteading community, though initial reactions mixed curiosity with continued skepticism. Some settlers attributed John's success to unusual weather conditions or measurement errors, arguing that one night's testing couldn't overturn generations of proven frontier practice. Others began quietly planning their own thermal mass experiments for the following winter, recognizing that 50% fuel savings could mean the difference between survival and failure during the harsh prairie seasons that lay ahead. By February of 1893, a secondary problem emerged that threatened to undermine the stone wall's remarkable efficiency. Despite the thermal mass storing and releasing heat as designed, John discovered that cold air infiltration through his cabin's log joints was stealing warmth faster than the wall could replace it. On a particularly windy night with temperatures at minus 12 degrees Fahrenheit, he measured interior air temperature at 67 degrees at 9:30 in the evening, but by 3 in the morning it had dropped to 60 degrees despite the stone wall's continued heat output. The culprit revealed itself during daylight inspection. Prairie winds driving through gaps between logs created subtle but persistent air currents that carried heated air out of the cabin while drawing cold air inward. The standard mud and grass chinking between logs, which had seemed adequate during construction, had dried and cracked during the winter's freeze-thaw cycles, opening hairline gaps that became highways for heat loss. Additionally, the single-pane windows radiated warmth directly through the glass, while the main door's threshold allowed cold drafts to sweep across the floor each time he entered or exited the cabin. Anders Johansson, the Scandinavian mason who had initially doubted the stone wall concept, offered a solution drawn from his homeland's harsh climate experience. In Norway and Sweden, builders used a technique called backchinking, where thin oak shingles were driven into log gaps from the interior side, then sealed with a specialized mortar that could flex with temperature changes without cracking. This method created a double barrier against air infiltration while allowing the logs to expand and contract naturally. Johansson demonstrated the technique using hand-split oak shingles, each about 4 inches long and tapered to a thin edge that could be driven deep into the gaps between logs. The shingles were positioned so their grain ran vertically, allowing them to compress slightly as they absorbed moisture from the mortar while maintaining their seal. Once the shingles filled the major gaps, Johansson applied his special mortar mixture, combining local lime with sand, clay, and dried moss collected from north-facing rocks, where it remained green throughout winter. The moss component proved crucial to the mortar's performance. Unlike standard clay-based chinking that became brittle in extreme cold, the moss fibers provided flexibility that allowed the mortar to bend rather than crack when logs shifted during temperature changes. Johansson explained that Scandinavian builders had discovered this technique centuries earlier, when standard mortars failed repeatedly during harsh northern winters until they learned to incorporate organic fibers that moved with the wood. Addressing the door presented a different challenge that required borrowing from indigenous building knowledge. Yellow Feather had described how Plains tribes constructed double-flap entries to their winter lodges, creating an airlock system that prevented cold gusts from reaching the interior fire when someone entered or left the shelter. Mary Harris, the widow homesteader, had attempted her own version of this concept by building a small enclosed entry to her cabin, though her execution lacked the thermal understanding needed for maximum effectiveness. John designed a vestibule measuring 4 feet deep and 6 feet wide, constructed as an addition to his cabin's main door. This created 2 separate entries, first into the vestibule from outside, then from the vestibule into the heated cabin interior. The key innovation involved timing and thermal dynamics rather than simple construction. When entering from the cold, a person would step into the vestibule and close the outer door before opening the inner door, preventing the direct flow of cold air into the heated space while allowing the vestibule to serve as a thermal buffer zone. The window improvements required more sophisticated techniques, borrowed from Eastern building traditions that were slowly reaching the frontier through railroad connections. John installed storm windows by mounting a second pane of glass 2 inches outside each existing window, creating an insulating airspace that dramatically reduced heat loss through radiation and conduction. The air gap between the panes acted as a thermal barrier, similar to the principle behind his stone wall, but applied to glass surfaces. Heavy wool felt curtains provided the final element of window insulation. These curtains, sewn by Mary Harris using wool from local sheep, extended from ceiling to floor and could be drawn closed at sunset to create an additional thermal barrier against nighttime radiation loss. The felt's dense fibers trapped air while blocking radiant heat transfer through the glass, effectively creating a third layer of thermal protection. Testing the complete envelope system during a 3-day cold snap in late February revealed the cumulative power of these seemingly minor improvements. Outside temperatures dropped to minus 25 degrees Fahrenheit, with sustained winds of 15 miles per hour, conditions that would typically overwhelm any frontier heating system. John followed his established routine, burning his fire until 9:30 in the evening, then allowing it to die completely while relying on stored heat and improved insulation. The results exceeded his most optimistic expectations. Interior temperature at 9:30 measured 68 degrees Fahrenheit, identical to previous tests. However, by midnight the temperature had dropped only to 66 degrees, and by 6 in the morning it measured 63 degrees Fahrenheit. The total overnight temperature drop of 5 degrees represented a dramatic improvement over the previous month's 8-degree loss, achieved during more severe weather conditions. More significantly, the fuel consumption during this test period dropped to 3/4 of a cord per 24-hour cycle, compared to the 1 full cord required before the envelope improvements. This additional 25% reduction, combined with the original 50% savings from the thermal mass system, meant John was now using less than half the firewood required by standard frontier cabin heating methods. The envelope improvements also eliminated the subtle discomforts that had persisted despite the stone wall's heat storage. Cold drafts across the floor disappeared entirely, the interior humidity remained stable. Without the dry air conditions that plagued most heated frontier buildings, and frost formation on interior surfaces became impossible due to the consistent temperature maintenance. Sam Roberts visited during the testing period and observed that John's cabin felt fundamentally different from standard frontier accommodations. Instead of the typical hot zones near the fire and cold zones away from it, the temperature remained surprisingly uniform throughout the interior space. The combination of thermal mass storage and controlled air movement had created what Roberts described as the most comfortable winter quarters he had experienced anywhere on the Montana prairie. By April of 1893, the seasonal transition exposed a fundamental flaw in John's heating system that threatened to waste the gains achieved through thermal mass and envelope sealing. As daytime temperatures climbed above 40 degrees Fahrenheit, while nights still dropped to 25 degrees, the cabin began exhibiting troublesome temperature swings that revealed inefficiencies in how the fireplace captured and distributed heat from the burning wood. The problem manifested most clearly during the warmer spring days, when solar radiation through the south-facing windows combined with heat radiating from the stone wall to push interior temperatures above 75 degrees Fahrenheit by mid-afternoon. Yet when evening arrived and temperatures dropped rapidly, the cabin still required significant fire input to maintain comfort through the night. John realized that much of his fire's energy was escaping up the chimney as hot exhaust gases, rather than transferring into the stone mass where it could be stored for later release. Pete Hansen, the frontier blacksmith whose shop served homesteaders throughout the region, had observed similar problems in other heating installations and suggested a solution based on European metalworking techniques he had learned from Austrian immigrants. The issue lay in the fireplace's configuration, which directed hot combustion gases straight up and out of the cabin rather than forcing them to make extended contact with the thermal mass wall. Hansen proposed repositioning the fireplace opening 6 inches, forward from its current location, creating space behind the firebox where hot gases could be redirected before exiting through the chimney. This modification would require constructing what he called a flue diverter, a custom fabricated metal assembly that would channel exhaust gases through a longer path behind the stone wall, allowing more heat transfer into the mass before the gases finally escape to the outside air. The flue diverter itself represented sophisticated metalwork that pushed the boundaries of frontier craftsmanship. Hansen forged the main components from heavy sheet iron, creating a series of baffles that forced hot gases to travel horizontally behind the stone wall before turning upward toward the chimney exit. The gas path extended approximately 6 feet horizontally through channels built into the wall's back side, more than tripling the contact time between hot exhaust and thermal mass compared to the original straight-up design. Installation required partially dismantling the upper portion of the stone wall to create horizontal passages for the gas channels, then rebuilding with careful attention to maintaining structural integrity while accommodating the new heat recovery system. Klein supervised this delicate work, ensuring that the stone courses above the gas channels remained properly supported while the channels themselves were lined with fire-resistant clay to prevent heat damage to the surrounding masonry. The seasonal control challenge demanded a different approach entirely, one that drew inspiration from Austrian masonry heater traditions that Karl Becker, another immigrant craftsman, had learned in the Alps. European builders had long recognized that heating systems optimized for winter survival could become problematic during spring and summer months when external temperatures made indoor heat storage counterproductive rather than beneficial. Becker recommended installing a summer shutoff damper in the main chimney, a hinged metal plate that could reduce the chimney's effective cross-sectional area by approximately 40%. This damper allowed fine control over draft conditions, enabling John to slow the flow of gases through the heat recovery channels during milder weather while maintaining proper combustion air supply. In summer months, the damper could be opened fully to provide maximum ventilation and prevent heat buildup in the stone mass. Complementing the damper system, Becker designed adjustable vents positioned near the cabin's ceiling and floor that could modulate air circulation patterns based on seasonal needs. During winter, these vents remained closed to prevent heat loss, but during spring and summer, they could be opened to promote air movement that would carry away excess heat while maintaining comfortable living conditions. The vents incorporated sliding wooden panels that allowed precise control over airflow volumes. The indigenous knowledge contribution came through continued consultation with Yellowfeather, who described seasonal adaptation techniques used in Plains tribal architecture that white settlers typically ignored. Buffalo Hunter lodges incorporated removable wind panels and adjustable covering systems that could be modified throughout the year to optimize thermal performance for changing weather conditions. Adapting these principles to log cabin construction, John installed hinged wooden shutters on his south-facing windows that could be adjusted to control solar heat gained during different seasons. In winter, these shutters remained open during daylight hours to capture solar energy that would supplement the stone wall's heat storage. During spring and summer, the shutters could be partially closed to prevent excessive solar heating while still providing adequate daylight for interior activities. The removable windbreak concept evolved into a series of hinged wooden panels that could be positioned outside the cabin's walls during periods of harsh wind. These panels, constructed from split oak boards, could be quickly installed to deflect cold gusts away from the cabin's exterior surfaces, reducing convective heat loss through the walls and windows. During calmer weather or when wind direction favored the cabin's orientation, the panels could be removed and stored to avoid unnecessary obstruction of airflow. Testing the complete heat recovery and seasonal control system began in early May 1893, during a period when daytime temperatures reached 50 degrees Fahrenheit, while nights still required heating for comfort. John operated his modified fireplace for 3 hours each morning, with the flue diverter directing exhaust gases through the extended path behind the stone wall and the chimney damper adjusted to optimize gas residence time in the heat recovery channels. The results demonstrated remarkable improvement in fuel efficiency and temperature control. Interior temperature at 8 in the evening measured 71 degrees Fahrenheit, achieved with only 3 hours of morning burning compared to the 6 hours typically required under the previous system. More impressively, overnight temperature drop measured only 4 degrees, from 71 degrees at bedtime to 67 degrees at sunrise, despite outside temperatures falling to 25 degrees Fahrenheit. Total fuel consumption for the 24-hour test period measured 3/4 of a quart, representing a 25% reduction compared to the previous spring's consumption using the unmodified system. The heat recovery improvements had captured energy that previously escaped as waste heat, while the seasonal controls prevented afternoon overheating that had required opening doors and windows to maintain comfort. The afternoon overheating problem that had plagued earlier tests disappeared entirely through coordinated use of the window shutters, adjustable vents, and controlled solar gain management. Interior temperature remained stable between 68 and 72 degrees Fahrenheit throughout the day, eliminating the temperature swings that had made the cabin uncomfortable during transitional weather periods while maintaining the thermal mass system's ability to carry stored heat through the cool prairie nights. The winter of 1894 brought conditions that tested every survival system on the Montana prairie beyond its designed limits. Beginning in late November, a persistent high-pressure system settled over the northern Great Plains, trapping Arctic air masses that pushed temperatures below -15 degrees Fahrenheit for 15 consecutive nights. Sustained winds of 20 to 30 miles per hour drove the effective temperature even lower, while snowdrifts accumulated to 4 and 5 feet deep across the open prairie, blocking roads and isolating homesteads from supply lines and mutual assistance. The regional crisis deepened when the railroad freight system collapsed under the severe conditions. Rail lines froze solid east of Miles City, stranding 3 supply trains loaded with cordwood and heating coal intended for frontier settlements. Local woodcutters found themselves trapped by impassable drifted roads, unable to reach timber stands or deliver split wood to customers who had planned to purchase fuel through the worst months. Many homesteaders faced the prospect of burning furniture, fence posts, or anything combustible to maintain minimal heating as their carefully stockpiled wood supplies dwindled faster than anticipated. Standard frontier heating systems failed catastrophically under these extreme conditions. Sam Roberts, whose cabin lay 400 yards south of John's homestead, burned through 30 cords of split oak during the 15-day crisis period, yet still recorded interior temperatures dropping to 38 degrees Fahrenheit on 3 separate nights. His family slept fully clothed under multiple layers of blankets, and water buckets froze solid despite placement within 6 feet of their continuously tended fire. The constant fire-stoking schedule required someone to rise every 2 hours throughout each night, leaving the family exhausted and increasingly unable to maintain adequate heat output. Mary Harris faced similar struggles in her cabin to the north, where improved wall construction provided some advantage over completely standard buildings, but still demanded 25 cords of fuel during the same period. Her interior temperature averaged 12 degrees Fahrenheit lower than her fire-tending efforts intended, and she suffered the loss of 3 chickens when her barn door mechanism froze shut, preventing access to feed and water during critical morning hours. The accumulated repair costs from frozen pipes, door hardware replacement, and livestock losses reached $20, representing nearly 2 months of typical frontier income. John's integrated thermal system performed under these conditions according to design parameters established during the previous 2 years of testing and refinement. His total fuel consumption during the 15-day emergency measured 15 cords of split oak, exactly half the amount required by Roberts's standard cabin, and 40% less than Harris's improved but thermally limited structure. More significantly, his interior temperature never dropped below 65 degrees Fahrenheit at any time during the crisis, starting each evening at 68 to 70 degrees and declining to a minimum of 62 degrees before dawn. The elimination of nighttime fire tending proved crucial during the extended emergency. While his neighbors exhausted themselves with round-the-clock fuel management, John maintained normal sleep patterns, rising each morning rested and capable of handling the daily challenges of severe weather survival. His water supply remained liquid throughout the crisis, his door mechanisms operated normally, and he experienced 0 equipment failures or repair costs related to freeze damage. The performance differential became impossible to ignore when neighbors began visiting John's cabin during the worst nights, seeking temporary refuge from the brutal conditions in their own homes. Roberts brought his family to John's cabin on the night of December 10th, when outside temperatures reached minus 28 degrees Fahrenheit with 40-mile-per-hour winds. They discovered an interior environment so stable and comfortable that Roberts later described it as like stepping into a different season entirely, warm air that stayed warm instead of hot spots and cold corners. Word of these results spread through the scattered homesteading community as soon as travel became possible again. The County Homestead Association, which maintained records of fuel consumption and winter survival rates for insurance and territorial development purposes, requested detailed documentation of John's system performance during the crisis. Their secretary compiled comparative data showing that thermal mass cabins used an average of 50% less fuel than standard construction while maintaining superior comfort and eliminating cold weather equipment failures. The technical validation extended beyond simple fuel efficiency measurements. Association investigators noted that John's cabin exhibited none of the humidity problems that plagued most frontier winter quarters, where condensation from heating and cooking created persistent dampness that fostered mold growth and structural damage. The thermal mass system's gentle, consistent heat release eliminated the extreme temperature variations that caused condensation cycles, preserving both structural materials and stored food supplies that often spoiled in other cabins during long cold periods. Regional adoption began immediately following the crisis winter, as established homesteaders and new arrivals alike recognized the survival advantages demonstrated by John's integrated approach. The Homestead Association published detailed sketches and specifications in their 1895 Winter Efficiency Circular, distributed to over 300 frontier properties across central Montana and adjacent territories. Local suppliers modified their standard chinking materials and began stocking lime mortar and stone cutting tools, specifically for thermal mass construction projects. Pete Hansen found his blacksmith business transformed by demand for flue diverters and seasonal damper systems as settlers throughout the region sought to upgrade existing fireplaces with heat recovery improvements. He trained 2 apprentices specifically in the metalwork techniques required for thermal system components, establishing a regional craft specialty that spread to other frontier blacksmith shops across the northern Great Plains. Archaeological surveys conducted during the early 20th century documented the widespread adoption of John's innovations. Preservation teams examining surviving prairie cabins built between 1895 and 1915 discovered thermal mass walls behind fireplaces in 47% of structures, compared to less than 5% in cabins built before 1894. The geographic distribution of these features clustered around Homestead Association distribution networks, confirming the role of technical documentation in spreading frontier building knowledge. Modern building science research validates the fundamental principles John discovered through traditional knowledge synthesis and empirical testing. Contemporary studies of thermal mass performance in cold climates confirm that heavy interior walls can reduce heating fuel consumption by 30 to 60% compared to lightweight construction, while maintaining more stable interior temperature profiles that improve both comfort and structural longevity. The integration of multiple thermal strategies, mass storage, envelope sealing, heat recovery, and seasonal control represents sophisticated building system thinking that parallels current high-performance construction approaches. John's achievement lay not in any single innovation, but in recognizing that traditional knowledge from multiple sources could be combined systematically to address the specific challenges of prairie winter survival more effectively than conventional frontier building wisdom. The legacy of 1894's trial winter extended far beyond individual homestead improvements. It demonstrated that frontier settlers could enhance their survival prospects substantially by respecting indigenous thermal management knowledge, adapting Old World craft traditions to New World conditions, and approaching building challenges through systematic integration of proven principles, rather than reliance on simplified conventional solutions that worked adequately under normal conditions but failed catastrophically when tested by extreme weather events.